All right, so I can hear everything that you say on that video camera. You ready for that? So I am not. You gave the disclaimer, I do not like videos. So one thing I just want to remind you about was that little analogy that we talked about yesterday. So remember the analogy of starting out with my little Pictionary. Here you have my tree, right? You can understand that. And on that tree you may have some apples. And then I'm pretty sure I had a nice looking dagger. That served as my tool to cut off these apples. But wait, do we just want those apples to fall to the ground if you're an apple farmer? No. Probably not. You would prefer that they get transported So here's your transport vehicle, and they make the way to the market, and at the market the apple farmer will then trade their apples for what they want, which is money. So this is just transforming one resource to another resource. So very similar with energy. So filling in more specifics about what all of these represent. The big tree, big complex organic compound, is supposed to represent glucose. And the things that will be harvested from glucose, these little apples are supposed to be your hydrogen atoms. And remember that each hydrogen is really a hydrogen ion, which is a proton. Just put that. As well as an electron. So whenever you see an H, that represents a proton and an electron. You will need to harvest those and put them on your transport vehicle. And the electron carrier for metabolism is going to be called what? What three-letter word? NAD. So NAD. So NAD on its own can be loaded up with its harvest. 2 hydrogens can be carried on NAD. Remember, I cheated with the notation. So it's just to signify that you do have 2 hydrogens able to be carried, meaning 2 protons and 2 electrons. With NADH2, is this the oxidized or reduced form of NAD?
Reduced.
So this will be reduced. It does have the extra electrons here. Will this be the more energetic or less energetic form of NAD?
More.
Okay, so it's the more energetic, which means it has the most potential to get more energy. So again, think back to what you know. Would an empty truck have more potential for money, or a full truck have more potential for money? So you want a truck that is loaded up to get you what you want at the very end. And instead of money at the very end, what we're looking for with metabolism is ATP. And then the last thing to fill in is, what is the market where these hydrogen ions and electrons will be transported to produce that ATP? So what is that specifically called? This will be your electron transport chain. So the ETC. Because the ETC is where you're going to deposit your H into that electron transport chain. The H will be separated into protons moving outside the membrane and electrons moving within the membrane. But they will be transformed into the energy molecule that the cell really wants, which is ATP. All right, so you got that? Memorized, good. Then we're going to erase that beautiful artwork. And pretend, what if we did start with 1 molecule of glucose? There are 3 major pathways that can break down glucose. One is going to be called aerobic respiration. One is anaerobic respiration. And the third will be fermentation. Only one of these takes place in the presence of oxygen. That would be aerobic. So this will only take place in the presence of oxygen. These will only take place in the absence of oxygen. So minus O2. And let's look at aerobic respiration more specifically. Aerobic respiration has 3 major pathways underneath it. So the first you would think of is glycolysis. Second, Krebs Cycle. And the third will be the ETC, or electron transport chain. You'll have the same pathways here in anaerobic respiration. And fermentation even starts out with glycolysis. Should shorten my arrow here. However, the second step here is going to be just a fermentation reaction or reactions, maybe 1 to 2 reactions at the most. All of these have in common that they will all lead to the production of ATP at the very end. But they will typically produce different amounts. So how about fermentation? How many will it produce net? Just 2. So you do not get a lot of energy by way of fermentation. Compare that with aerobic respiration, which has, for bacteria, 38. Mitochondria also produce 38. But when the mitochondria are in a eukaryotic cell, remember mitochondria have to transport that ATP across the membrane. And so that will cost them 2 ATP. Anaerobic respiration is variable. However, for our class, we're really going to focus on it not being as efficient as aerobic. So we'll just simplify it to say it's never as efficient as aerobic, and so we'll just say it produces 2. So similar in that they both all produce ATP, different in the amounts. One thing here would be, one thing is different for all of these, and that would be that final electron acceptor. So the final electron acceptor for aerobic respiration is going to be oxygen. So oxygen will be hanging out here. For anaerobic respiration, it will be an oxygen-containing ion, but not oxygen itself. So sulfate or nitrates. And then for the fermentation reaction, it's usually some organic molecule. And common ones would be pyruvic acid or lactic acid, as accepting the final electrons. All right, one thing I do want to say is anaerobic respiration is a highly specialized process, and it's not very common in, well, it never happens in humans, and it's just not as common of a pathway as aerobic respiration and fermentation. So this is all I will require you to know about anaerobic respiration, right? Just what the pathways are that it encompasses, what its final electron acceptor would be, and about how much oxygen or how much ATP would be produced. And what I was thinking in my mind was also to mention it occurs in the absence of oxygen. Just saying that before my mind gets there. So to simplify this diagram, I'm going to erase that. Since I mentioned that's all we'll talk about with anaerobic respiration would be those basics. Now let's look at a little more detail with aerobic respiration and fermentation. And I did mention that glycolysis is really 10 different reactions. You don't have to memorize that. But I do want you to realize that even though I have it as just one single arrow, I have just folded in 10 different chemical reactions within here. And I'll show you what those 10 different chemical reactions would look like. And the Krebs cycle is about 8. Electron transport chain, probably 15 to 20 different reactions. Which means for every chemical reaction, there will be a unique enzyme. All right, now we're just going to focus on the starting reactant and what we're going to put into glycolysis. So the starting reactant for glycolysis would be glucose. So you'll put in glucose. Glucose is a 6-carbon sugar, meaning it has these 6 black spheres, 6 carbons. And after glucose goes through glycolysis, then you are left with 2 molecules of pyruvate. So pyruvate or pyruvic acid, does not matter if it's in the ester or acid form. But pyruvate is shorter for me to write. Hence, that's what I'm using. And you never gain or lose carbon. So starting out with 6, just break them apart. Now you have 2 molecules of pyruvate. These pyruvate will be what goes into the Krebs cycle. Remember, my Krebs cycle nickname is the Chop Shop. And that's because this is where a lot of chopping and harvesting takes place. You'll have that chopping apart of this whole molecule. Chop, chop, chop. Harvest, harvest, harvest. All of these hydrogens will be taken off. Every single carbon will be broken apart. So they will be harvested down to their bare framework, which will leave this pyruvate now as carbon dioxide. So you have these very tiny units of carbon, just one carbon. And if you started out with 6 carbon here in your glucose, how many molecules of carbon dioxide would you predict? 6. Yep. And this carbon dioxide is just going to be excreted as waste. Will the carbon dioxide be going into the electron transport chain? No. So it's not going to progress into the electron transport chain. Something else will, though. So I'm going to erase those numbers of chemical reactions. Now I'm just going to continue using green for ATP, because this is the many that we want to make. And mention that we will get out some ATP directly from glycolysis. So you will be able to net 2 ATP, a little, but not a whole lot. And I will say this is net. The Krebs cycle, you will also get some energy out of the Krebs cycle. 2 ATP, which means if you get 38 ATP total out of aerobic respiration, how many ATP are coming from the electron transport chain? 34. So you can see that the electron transport chain is the big money market. That's where you're getting a lot of ATP produced. All right, the last thing we'll look at here will be those NADH molecules. So you did harvest some hydrogen off of the initial split of glucose, and you will get a couple of NADH2 out. But would you predict you'll get more NADH2 out of the Krebs cycle or less than glycolysis? Okay, so this is what's happening. Start with glucose, assembled. I split it into 2 for glycolysis, 2 pyruvate molecules. When it goes into the Krebs cycle is the chop shop. That's where you're tearing this molecule apart and harvesting a whole bunch of hydrogen, right? Harvest, harvest, and I'll get my little truck up here to contain my hydrogens. So can you see with the Krebs cycle, that chop shot, you're going to tear apart that pyruvic acid molecule, which allows you to harvest a whole bunch of H, put those on your electron carriers or your hydrogen carriers. And in fact, you'll be able to harvest a lot of H. So quite a bit of hydrogen is harvested. We'll also see there is also hydrogen carried on another electron carrier known as FAD. Works the exact same way as NAD. So whenever you see it, just think of NADH. What happens to this NADH? So when you're thinking of NADH, thinking, that's my harvest loaded on the carrier. Now what? Now it's going to be transported to the market. The market is the electron transport chain. So these NADH will be transported down to the electron transport chain. and dropped off. So they will drop off their H, be unloaded, and go back to pick up more. What happens to these NADH? Same exact thing. So they are just loaded carriers going to the same exact market. So all of these electron carriers will be carried to the electron transport chain, and these hydrogen will then be exchanged for ATP. And we'll look at that in more detail. What happens to this ATP up here? Does it go to the electron transport chain, or is it just used up for work? So it is just used up for work as soon as it's produced. All right, so that's the basics of aerobic respiration. We'll really focus on just the beginning and the end. Okay, so, but the same thing really is occurring in all the different steps. Harvesting and then exchanging your harvest at the market for the product you want. Fermentation, same exact thing with glucose being broken down. So glucose being broken down into 2-pyruvate. What did we say would happen to those pyruvate? They would be entered right into the fermentation reaction. Does glycolysis produce any NADH over here? The exact same glycolysis. So whatever is happening at that type of glycolysis, it's the exact same process as glycolysis occurring in fermentation. Will you have any ATP produced by glycolysis? Yep, you will have a couple of ATP produced. Now, a problem is, here you have your H loaded on the carrier, but we really don't have a market, right? Don't have the electron transport chain. So these H have to be unloaded somehow, because if you don't have any unloaded ones to put into glycolysis, then glycolysis will stop. So you have to be able to load and unload. And that is actually going to be the job of the fermentation reaction. So what will happen here is these hydrogens are actually going to be transferred to pyruvate. And 2 extra hydrogens on pyruvate equals lactic acid. So lactic acid is just a pyruvate with an extra H. They're very, very close in structure. Did the fermentation reaction generate any ATP? No. The only benefit is that you unload NAD, and now NAD can go back to glycolysis, load up, be unloaded, load up, be unloaded, so that this remains a sustainable cycle. If you don't unload the carrier, you're stuck. Even though 2 ATP is not a lot of ATP, it's better than 0 ATP. It's life or death. 0 death, 2 life. Okay? So now let's look at more details of glycolysis, the Krebs cycle, electron transfer chain, and the fermentation reaction. That's what we'll do on those worksheets.